we're going to use what we've learned about the derivative to make some graphs. We don't have to theoretically know how to graph or have functions in order to create a graph. We can use calculus. So where calculus comes in handy, in our first situation here, we can probably deal with this. We probably have enough background with quadratics to know how to factor this, to find the x-intercepts, to locate the vertex, and really get a good idea of what this graph looks like. However, many of us in college have not learned how to deal with something like this. Higher order polynomials, where we're not going to be factoring and finding x-intercepts. And there's a whole bunch of other things that are going on. Maximums, minimums locally, points of inflection, what we call critical points. We can't do this, well, we can with Desmos or graphing calculator, but in a test situation or something like that, we want to be able to just use the math to figure it out. And before we move on to the next slide, just answering this question, when we're given an equation of a function f of x, what can we get? Well, you can always usually get the y-intercept. Here it is, remembering that if we want to find the y-intercept, we set x equal to 0, and then we solve for f of x. And whenever you have those x's, it's always going to be that leftover constant. And here's a y-intercept in the cubic, which we can also still find. Sometimes we can find the x-intercepts if it's quadratic, and we can use factoring to do that. That's great. But really, we're going to rely on f of x only, maybe for some of the intercepts, and everything else is going to come from calculus. We're always like, what is f prime of x? What is a derivative of a function? What is it? And we're always come back at you, it's the slope. It's the slope of that function at any point in time. So let's break that down a bit. So if we have a slope that is positive, what does that mean? That means the function must have been going up, increasing. That's how you get a positive slope. If f prime of x is positive, that means the function is increasing. No matter where it is on the graph, it's going up. If f prime of x is negative, the function, no matter where it is on the graph, is decreasing. And if it is neither positive nor negative, that means you're at a local maximum or a local minimum, a high or a low. And I throw around these words local all the time. Local just means within the scope of what I'm looking at. Like for here, this is local in the first graph because my function's there. Now, this function might go off and do something crazy like this, and maybe this would be a global maximum up here, and we're heading down to a global minimum somewhere. But local just means within the scope of my investigation. All right, so this is my function. It's crazy looking, and we're going to look at each of the points and try and figure out, what the slope is doing. So this is f of x on this graph, and I'm going to do a very, very rough graph of f prime of x. And it's rough because I don't have an actual equation, so I can't figure out the actual slope at any of these points. I'm just eyeballing it. So looking at point A, we see that the function is decreasing. So it means the slope is going to be negative. And it's quite steep. So let's just say maybe the slope is something around here. Totally guessing. When we go to point B, we're at the bottom of a valley. It's flat. If I draw a line tangent, that gives me the slope. That's 0. So when we get to B, we can commit to, we know that's 0. When we head to see what's happening, the function, although it's in the negative, it is increasing. The value of the function is negative, but the slope of the function is positive. So, I don't know, let's put a point here. When we go back to D, we're at a maximum. Our slope is 0. And as we head down to E, our slope is negative. We're going down quite steeply. So maybe, I don't know, E would be something like this. Nothing is happening when x is equal to 0. That's an asymptote. All right, heading over to F, what do we have? we have, and even though the function is negative, so it's hard to look at these sometimes, it's increasing. So the derivative will be positive. It's increasing quite steeply, let's say here. And then when we go to g, the function is still increasing at this point, but it's much more shallow. So the slope is positive, but it has a lower value. Is what I draw what this derivative looks like? No, not necessarily. Maybe kind of. Something like, oh, that. And this one would probably do something like this. Very, very rough, but just to get an idea that f of x is telling us about whether the function, f prime of x is telling us about whether the function is increasing or decreasing. So we're going to bring in those two functions we started with again, and we're going to talk about how to find their local maximums and minimums. So once again, those local maximum minimums are the tops of the hills, the bottoms of the valleys in the area that we're looking at. Okay, so our steps will always be differentiate. So I'll say find the derivative, and then set the derivative equal to 0, and then solve for x. Okay, I've put a couple of number lines here to help us along. So once again, this one's a quadratic, the first one, number 1. We could have done it without it, but we are going to use calculus, not algebra. 2x minus 2. Okay, we have found the derivative. So we are going to find a maximum or a minimum when that slope is equal to 0, which means when f prime of x is equal to 0, and we solve for x. We move the negative 2 to the other side, divide by 2, we get x is equal to 1. Okay, so this is my number line. Here's 0, here's 1. So when x is equal to 1, we have something cool happening. It's either a maximum or min. So there's a few things it's always a good idea to do. It's always a good idea to find the actual coordinate of that point. So I'm going to figure out, I know x is 1, but what is y? So I go back up to this, and I find f of 1. What is y when x equals 1? So I'm getting the y coordinate of that point. So we do 1 squares minus 2 minus 15 gives me negative 16. So I know this point is actually 1 comma negative 16, but I'm just on a number line. So I'm going to try and stay away from that. All right, what else do we need to know? We need to verify that this is actually a maximum or minimum. Let's look at what that could be with a picture. So here's a maximum. And what do we notice? The function is increasing to the left and decreasing to the right. So the slope would be positive to the left and negative to the right, and 0 right at our point. If you are a minimum, it's kind of the opposite. We're decreasing to the left and increasing to the right. So we expect f prime of x to be negative to the left and positive to the right, and 0 at the minimum. Okay, well, knowing that, we can use some test values to figure something out. So here's the left, let's say f prime of 0, and to the right, let's say f prime of 2, and all I'm doing is figuring out whether the slope when x is 0 is positive or negative. So I'm going to use this equation, 2x minus 2. 2 times 0 minus 2 is going to be negative, and the value doesn't really matter to me at this point. I just want to know what's going on. And then I test over to the right of number 1. Now I could use 1.2, 1.3. I'm lazy. I'm using things that are easy for me to do in my head. 2 times 2 minus 2 happens to be 2, which is positive. Okay, so I have the situation where I'm negative to the left, I'm coming down and going up, so this is a minimum. So I've found in my first equation there is one local minimum which occurs at 1 comma negative 16. Let's look at a more complicated one. Number 2. So first things first, we've differentiate, find the derivative using just the power rule here. 3x squared minus 18x, and then we're going to have plus 15. Okay, this one looks like it's going to be factorable. Minus 6x plus 5. Okay. And within the brackets, x minus 5, x minus 1. Great. What did I have to do? I had to know when the right side is equal to 0. When the slope is equal to 0, because that tells me that I'm at a maximum or a minimum. And in this case, there's two times that happens. X could be equal to 5, or x could be equal to 1. So we'll put our 0 back here, and I'll put a 1, 2, 3, 4, 5. So I have 1 and 5. And I know I have exciting things happening at these points. All right, let's get our coordinates first. So I'm going to find f of 5. Going back to the original equation, it can get confusing. So 5 cubed minus 9 times 5 squared, minus 15 times 5, plus 1 should give me negative 24. So I know this point is actually 5 comma negative 24. That doesn't tell me anything about a maximum or a minimum. And then I'm going to have f of 1 cubed minus 9 plus 15 plus 1 should give me 8. And I have 1 comma 8. Now I can figure some things out. If I'm at 8 when x is 1 and I'm down to negative 24 when x is 5, my logic tells me that I'll probably have a maximum when x is 1 and a minimum when x is 5. But I should check it out. I should verify it, and we'll show you why later. So I'll do some test points, and I'll choose 0 and I'll choose 2. And remember, when I'm testing here, I'm wondering whether the slope is positive or negative. So I'm finding f prime of 0, which means I'm going to look at this equation. And I'm finding f prime of 2. And when I go through to f prime of 0, everything's going to disappear except for that 15, so it's positive. Not really that concerned about the value. And when I think of the derivative f prime of 2, I'm going to do that same math, same equation, 3 times 2 squared minus 18 times 2 plus 15, and that gives me a negative value. So what does that mean? Here, I am increasing. This must be a maximum, and when I'm at 2, I'm decreasing, and there's no other action in there, so this must be a minimum. There we go. Max and min. We may or may not have talked about higher order derivatives in a previous class, but they come in really nicely right here. So let's revisit. What does f prime of x tell us about f of x, the function, when the function is increasing or decreasing? Okay, so let's say, even let's get fancy, intervals of increase or decrease. And how does it tell us that? By being positive or negative. If f prime of x is positive, we're increasing. If f prime of x is negative, we're decreasing. If f prime of x is 0, we're at a local maximum or a local minimum. Now let's talk about the derivative of the derivative. So f double prime, fancy way with a 2 in it. What does that mean? I'm just going to take whatever I found to be the derivative and differentiate it again to find the double derivative. So what could f double prime of x tell us about f of prime of x? So it's still going to be intervals of increase or decrease, but it's of the slope. So it's going to tell us if the slope is increasing or decreasing. And it'll do that if f double prime is positive, the slope is increasing. And if f double prime is negative, the slope is decreasing. So the most important thing about this is, what does that look like when you're on a graph? So I'm going back to graphing f of x, a function. What does it look like when the slope is increasing? Well, there's one that's easy. Like if you start at a shallow slope, a shallow positive, and you go higher. So we have a low positive slope here. So let's say f prime of x. And by the time we get here, we're steeper, so we have a higher positive slope. So that f prime of x is increasing, and that means that the double derivative will be positive. Now, there's another situation that is not as intuitive, where the function, the slope is increasing, and it's when you do this. So here we have a high negative slope, and here we have a low negative slope. So as we move from left to right on the graph of f of x, we're going from a very negative number to a less negative number, and that is increasing. Let's consider what it is when f prime of x is decreasing. So we're going to have f of x again. Once again, the easiest one to think about is in the positive. So if we start steep, the high positive slope, and our function ends up kind of tapering off and has a low positive slope, then we have f of x, or f prime of x, is decreasing. The slope is decreasing, even though the value of the function itself is increasing. The slope is decreasing. And then our other situation that creates that, so we do this. So here we had a low negative slope. And by the time we go over to the right, we have a high negative slope. So once again, the slope is decreasing, which means the second derivative will be negative. What have I made here? Pictures of concavity. If your graph is concave up, the second derivative is positive. If your graph is concave down, or frowny, so think of smiles and frowns, the second derivative is negative. What happens when you're changing between the two? We call that a point of inflection, and that's where f double prime x is equal to 0. All right, we're going to take this over to the graph. I'm just giving myself a little cheat to look at. If I draw a squiggle, I have, that tells me about, this is f of x. What is the second derivative doing? Here we have, because we are concave up, we would expect to see a positive second derivative. Here we would expect to see a negative second derivative. So let me just trace along that. Positive to this point, let's say, negative to this point, and give those some colors. And then we see this magical point, an inflection point, where we change from concave up to concave down, and we expect the second derivative to be 0 there. Okay, so we don't need to do this from the slope. We can do it directly from the function, obviously. So looking at my graph here, when I'm at A, the graph is concave up, and just draw your smiles and frowns to see this. So I'm expecting it to be positive at A, and this is, I'm talking about the second derivative now, not the first derivative. Looking at the concavity, not the slope. All right, when I hit B, it's still concave up here, a little less steep. C is my inflection point, where I'm turning from concave up to concave down. So that gets to be 0. D is where the slope is 0, but it is concave down. So I expect a negative second derivative. And e also negative. So we get this kind of linear thing going on here, which I've totally ruined. Looking in the positive x area, so at points f and g, both of these are concave down. So we can see it if you draw the little hole shape. That helps you visualize it. So we would expect maybe something like this, a negative for f, and g would probably be getting closer to 0, right? The concavity would be decreasing. So we're back to our two equations, our two functions, with the first derivative already done for us, just like we found before. Now we're going to find the second derivative. So you're just looking one above you, you're taking the derivative of 2x minus 2, and that is just 2. So this is an always positive situation. Which means what? It means it's always concave up. Does this make sense? Yeah, this is a quadratic. It's always concave up. Let's go to our second one. The second derivative is going to be the derivative of 3x squared minus 18x plus 15, which is 6x minus 18. Now, we're going to try and solve for the point of inflections, because those are the cool things that are happening here. That happens, we switch from concave up to concave down or back when the second derivative is equal to 0. So this is what we're solving, and we get x equals 3. This is nice because when you use other systems, if you find roots and all that, it's really hard to pin down the inflection point. You can't normally locate it exactly, but calculus lets that do that. You do that because if I find now f of 3, it's going to give me the y value, and I can exactly locate that point of inflection. And when I do that math, so x cubed minus 9x squared plus 15x plus 1, I get negative 8. So we knew that our picture looks something like this, and now we know this point is exactly 3 comma negative 8. You should always test whether it's actually an inflection point, whether things are changing, do a test value. So you could move over and figure out what the second derivative is doing at a point to the left, which could be 2, and what the second derivative is doing at a point to the right, let's say 4. So I'm just picking a value, any value, to either side of x equals 3. And at 2, I see that the second derivative is going to be 6 times 2, 12 minus 18, which is going to be negative. And that makes sense, concave down. And on the other side of it, it's going to be 6 times 4 is 24 minus 18, which is a positive number, concave up, makes sense. So pulling it all together, what we got from each thing, from the function in the first one, we could get a y-intercept, 0 comma negative 15, just by subbing in x equals 0 and solving. We could factor and actually find our x-intercepts here, which were 5, 0, and we should remember this from our last course, negative 3, 0. Check with me if you don't. And then we found from our first derivative that we had a minimum at 1, negative 16, and that from our second derivative it was always concave up. So this is more than enough to graph it. In fact, we kind of had most of it from the first, from just the function itself. So we have 5, 0, and this is not going to work out well picture-wise. Negative 3, 0, our minimum happens, I don't know, somewhere way down here, let's say, not to scale, and we're concave up. So in theory, you know, this graph could look something like this. When we looked into our second equation, the cubic, we found from the function the y-intercept only. But we went to the first derivative and we found that we had a maximum at 1, 8, and we had a minimum at 5, negative 24, and that we had an inflection point at 3, negative 8. All right, so putting what we can on there. 1, 0 maximum, or 0, 1, 1, 8, 5, negative 24, not even going to happen. And we have an inflection at 3, negative 8. We can just get that. Here we go. Woo, yeah, that looks awesome. They should hire me for this. Boom. And roughly drawn using calculus.